Now, I've got several announcements. I may have given you some of these, but I've got a little more detail than I had before. So let me get going on this. First, maybe kind of like most important for right now anyway, is that sometime over the weekend we pass midterm, okay? Last week was the end of the first mini-term. This week's the beginning of the second mini-term. So if you're in any mini-term classes, second mini-term start today or tomorrow, whatever the first day they meet this week, okay? Well, what does that mean? That means we need that I will be required to submit a midterm progress report probably sometime this week, which means I need a grade. And I've only got one grade so far in this class, and that was from one paper. And I know you've had the first test for a little while, and hopefully you will be able to wrap up that, or get your paper in. Get me something in this week so that I don't have to put that you're failing at midterm. Because I know none of you technically are failing, but if they ask for that, I have no grades to back them up, I have to put that down. So try to get me something this week. Okay. So that's the first issue. Second issue is akin to that one, and that's my office hours change from now on. Not on Monday, Wednesday. Monday, Wednesday stays just like it was. Okay. On Monday, 2 to 6, and on Wednesday, 2 to 4. Okay. That stays the same. All right. By and large. Okay. The Tuesday, Thursday is what changes, because I had a first mini-term physical science class that went 1:15 until 5:45. So my office hours on Tuesday and Thursday were 11:15 to 1:15. Okay. My second mini-term physical science class, because some of the automotive students take it, they don't get out of their block schedule until 3 o'clock. So then I can't start the physical science class until 3:15, which means it runs until 7:45. Okay. So what that means is, for me, I'm here later, but for y'all, I have more office hours. I have now from 11:15 till 3:15, which is good for me too. The other part isn't so good, but it gives me more office hours in the middle. So now, step back to the exception to the rule, and that's tomorrow. Tomorrow, I think I probably mentioned early in the term, at the very beginning, that I would have one Tuesday that I'd have a doctor's appointment, and that's coming up tomorrow. Okay, it's at 10:40, which means I have to leave for labs at 9. I have to be there at labs for 9:40. I mean, I have to leave campus by 9 o'clock. So that affects my 8:30 class big time. Because of that, I will be adjusting the start times for my 8:30 class to 8:15, and I'll do that for 3 classes. I think it's either going to be, I can't remember what we decided, Tuesday and Thursday of this week and Tuesday of next week, I think is what we decided. So normally our office hours are 8 to 8:15 in the morning. Because I'm going to start early, it'll only 8 to 8:30 in the morning. For the next 3 classes, Tuesday, Thursday, and Tuesday, I'm going to start at 8:15. So I only have 15 minutes of office hours before I go to class. So usually nobody bothers to come by that early in the morning anyway. Okay. It's going to wipe out my 10 o'clock class, my trig class, completely. So what we're going to do is make up that trig class this coming Friday. Okay? So that's going to change my office on Friday. I'll be on this campus rather than the Birmingham campus, and I'll be in class, oh boy, what time did they say? 9 to 10:15 on Friday. Okay? So that's how that affects. So this week, office hours are a little squirrely because of making up classes and that type of thing. All right, but after that gets over with, things will be back to normal, whatever that is. Okay. And then, let's see, from then on, Tuesday, Thursday will be 11:15. Oh, the other part. Because my appointment is at 10:40, there's no way I'm going to get out of the doctor's office before 11. I mean, it just doesn't happen. Okay. And in fact, if they're running a little late, I could be well after 11, which means I can't be back here on campus by 11:15 when my office hours usually start. So I won't be back on campus. The earliest I'd be back would be probably 11:45, and it could easily be 12 o'clock or later. Okay, so Tuesday's office hours will start when I get back to campus after my doctor's appointment, and I don't know what time that'll be. Okay, so I think that covers all the modifications of things that are going to happen because of my doctor's appointment. And here's this. All right. Now, any other announcements that I can think of? I can't think of anything now. So, any questions on anything we had? Did you have?
Yes, I think it was number 54 in section 4.4.
Okay. It was a question. It is a question. Section 4.4, you said?
Yes, sir.
Okay. Boy, chapter 5 is a long chapter. There we go. 4.4. And this is in the homework exercises 7.
Yes, sir. Oh, no, it's number 54.
Huh?
It's number 54.
54, okay. But in the homework exercises.
Yes.
Okay. So this technically wasn't a homework problem because it is an odd problem. Okay. So this is, let me get my pen set up. Okay. This is page 293, I hope. All right. 4.4 exercises. And number, you said 54? 54. All right. It says find the average value of a function. Is that what the one you're asking about? Okay. Average value of a function over the given interval and all the values of x in the interval for which the function equals the average value. Okay, so the function they give you is f of x is equal to 4 times x squared plus 1 over x squared over the interval 1 to 3. Okay, and it wants the average value of that function. Okay, now, just to remind you, this is a long section. The average value of a function, if you don't have the book, but if you turn back to page 285, that gives you the definition of the average value of a function on an interval. Okay? So the average value, I'm writing all this in because we don't have the problem written down and it's not in the text anywhere. I mean, not on the slide set anywhere. The average value of a function, okay? The definition is 1 over b minus a times the integral of the function from a to b. Okay. Now, and I take it this was similar to one of the test questions, is that right? Let me just, to make sure this is going to give you what you need. That would be, yeah, like 7, and it is very similar to that. Okay. Just wanted to make sure it wasn't just looking like that. And I'll give you permission to kick yourself as soon as I do this, okay? All right. I don't want to watch it, but yeah, never mind. Okay. All right. All right. Now, the issue here is getting this thing integrated, right? So before we do, okay, let's take this function. I'm going to first distribute. Is that okay? So that function, f of x, when I distribute, is going to be 4x squared plus 1 over, plus 4 over x squared, right? Yeah, okay. Now, here's where you got to get your leg loosened up now. All right, let's split that into a fractional form. 4x squared over x squared plus 4 over x squared. Is that not legal in most states? Okay. I can't even read my writing there. Oh, that's an x squared. Okay. And here x squared will go into x squared one time. So this is written as 4 plus 4. And if it's okay, I'll write that in exponential notation, x to the minus 2. Is that all right? Okay. Now, I really didn't need to do the multiply through by 4. I just did. Now I'm going to divide it back out. Okay. So this will be, and you know what the B's and A's are, right? Okay. I'm not even going to fill those in. I'll let you do it later. No, let's go on and finish the problem. Since you asked for it, I'll finish. What is your B? 3 minus, what's your A? 1. That'll be the integral from 1 to 3 of, oh, I'm going to factor out the 4. So that's going to go in the numerator here. Is that okay? All right. And that would then be, if I factor out the 4, that would be 4 times 1 plus x to the minus 2. Right? I put the 4 out front, so our thing to integrate here is 1 plus x to the minus 2 dx. Isn't it? Okay? Now I bet you can handle that, can't you?
Yes.
Okay.
So from there you just take the antiderivative?
Yeah, just take the antiderivative. And the 1 will be x, and the x to the minus 2 will be a x to the minus 1 with a minus 1, you know, so yeah, that will all be doable. Anyone want to see it taken further? I can do it. There's no way to check the answer because it's not in the back of the book. We can do it if you want. Yay or nay? Huh? Oh, don't mind at all. Okay. In fact, I'm going to have you do it anyway. Okay. So what's 3 minus 1? 2. 4 divided by 2 is 2. Okay. Right. Okay. All right. Now, antiderivative of 1 is x. Antiderivative of x to the minus 2. You add 1.
Oh, x to the minus 1.
Over minus 1. So I'm just going to put the minus there. Is that okay? Okay, everybody? Okay? And I'll evaluate that from 1 to 3. Okay? It's going to be 2 times, let's plug in the 3 and see what we get. Tell me what to write. Well, let's do it one at a time. Plug in the 3 and you get 3, right? Minus, and that's 1 over x, it would be minus 1/3, right? Minus, and then with a 1 in there, that would be a 1. And minus a minus makes a plus. 1. All right. Okay. Now, I can add those two together. They go to 0. And this gives me, and there's a couple ways you can do this. I think I'll do it this way. 2 times, I'm trying to think the easiest way to do it. They're both easy, but, you know, I think probably the easiest, if I can get my pen to work. Here we go. Okay. It would be 6 minus 2/3. Right? That would be 5 1/3. Or, if you prefer it, 16/3. And I don't know what. They don't give the answer in the back, so I don't know. Let's see if they do in the instructor edition. They might. Let me see. I haven't looked back here in a long time. This is 4.4. Okay, I'm getting close. Ooh, I even passed it. 4.4. Nope, I don't even think my book has an even number of answers in the back. Worth a shot, but it's not there. I thought they did have it, but I guess I was wrong. Answers to odd number exercises. I don't think my book's that much different from yours. Let's see if it was before that. Nope. All I have is odd. But I'm pretty sure that's correct. And either one of these two answers would be perfectly fine. For me, for WebAssign, probably they wouldn't, but we don't do WebAssign. They only allow one correct answer, and the rest of them they say are wrong, even when they're right. Any questions about that? Does it make sense? And you didn't know how to do it, did you?
Yes.
Yeah. Okay. Yeah. Cheat a little bit. Find the easiest way. Any other questions? Good question, by the way. Probably helpful for the others too. Something else?
Number 3.
3 on that test too? Okay.
Turn right in after that one.
Okay. I've got to refine that test. Okay. Whoops. I'm in the wrong class. Test 1, number 3. Is this graph the function g of y is equal to y squared? Is that the one? Because I have several different tests, and I'm not sure I'm looking at the right one. Write the integral that represents the area between the graph, the y-axis, and the line y equal 2.
Yes.
Okay. Okay. I'm afraid I'm going to lose stuff, so I'm going to put that there. This here. I hope I can. I think I'll get everything back in order. I hate losing stuff. Okay. All right. Why you have this problem, I'll let you know. It was a multiple choice problem in the test bank, and they'd already drawn it for you, but it was just going to take up so much room to do, and then it was multiple choice. I don't like that, so I thought, well, let's just have them do it. So I will do the first part of it, and all along the way I'll ask you when it's okay to stop, and I'm going to stop before I give you the answer. Okay, so this is test 1, number 3. Okay. It says, graph the function g of y is equal to y squared. And we're going, okay, we're only going to be in the first quadrant here. I'll let you know that to begin with. Well, let's check off a few points. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, this is our y-axis here. Okay, we'll do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, we don't need all those. Okay, so doing g of y is, give me a point. Now your g of y is now x. Okay, so give me a y and tell me what g of y is. Pick an easy one. Easiest one. Easier. Huh?
0.
0. And what would be g of y? 0. Okay, there's your point at the origin. Okay, then that next one was pretty good. What were you going to say?
1.
And what would g of y be?
1.
1. Okay, there we have it. Okay. Next, y. 2.
4.
4. Okay, that would be right about there. Okay. Next one. Make it easy.
3.
3.
9.
5, 6, 7, 8, 9. would be right about 1, 2, 3, 4, 5, 6, 7, 8, 9, and that would be 3 about there. Okay, this is about the best I can do because we can't get the 16 here. Something like that, right? That's half a sleeping parabola, right? Now, we didn't do the ones on the bottom side because that wouldn't have been a function, would it? Okay? So this is only the top half. Okay? Now, we want to write the integral that represents the area between the graph. There's the graph. This is g of y is equal to y squared. Okay, there's the graph. Okay? Between the graph, the y-axis, that will be this one, right? And the line y is equal to 2. So that's the area that you're trying to do right there. And it doesn't say evaluate it, it just says write the integral that represents that. Okay? Now, how is an integral going to look anyway? Okay. Okay. So he's already said, I was going to say A to B, but he said 0 to 2, and that's right. What are those values of? Really? X here is going from 0 to 4.
Oh, yeah.
And those are y. Since those are values for y, then we're going to have a dy out there, aren't we? So, a dy would be represented by a little increment right here, right? And you would be doing this little strip here. I can't get it to be a strip. Okay? And the length of that strip would be the function y squared minus 0. And the thickness would be dy. And you sum all those up or integrate those from 0 to 2. Does that give you enough? Okay.
I was confused on that one.
What's that?
I was mixed up on that one anyway.
Yeah. But I didn't mind drawing the graph for you because in the test bank, the graph was already drawn. So I thought I'd just have you draw it. But since it might be a little bit of a problem, there it is. That's all we're to do is write the integral that represents the area here between y-axis, the function, y-axis, and y. Y is equal to that area. So just write the integral. And it's represented by the integration sign means sum of all these things, going from 0 to 2 of these strips. So you do this little one down here, the bigger one here, the here, and that would be the length of each of those strips would be from here to 0. Here, okay? And it's pretty easy from there on. I hope. Any questions? I can't do much more without giving you the answer. I've given you most of the answer right there. Any question? Okay, I didn't give it to you. Clark did. Whoever said called it out. I was going to leave A to B. Huh?
It's going to accuse me of cheating.
What's that?
You know that.
Yeah. Now, there is another way you could do it. I'm not recommending you do it that way, but there is another way you could do it. You could do your dx's this way, and then you'd be going from the length of this, if you did a little incremental x here, the length would be from 2 to the function, so it would be 2 minus, then you have to write that as a function of x, and x is equal to y squared. So doing that as a function of it, y is equal to square root of x. So it would be 2 minus square root of x, and you're going here from 0 to 4. You could do it that way, but I'm not recommending you do it. It's more complicated, but it's doable. Any questions? That's as far as I can go without giving you the answer, so I'm going to stop there. Is that okay? Okay. Any other questions? All right. Ready to get back to chapter 5. Okay? All right. Okay. Now, we did example 4. We're getting ready to start example 5. Page 376, chapter 5, which is logarithm, exponential, and other transcendental functions, and 5.7, inverse trigonometric function differentiation. Okay. Here was the function they gave you. Y is equal to arc sine of x. I'll write it the same way they do. I prefer saying inverse sine of x. Plus x onto the square root of 1 minus x squared. Okay. Now, it says take a derivative of that. It really doesn't say that. It just does the derivative of it. The title of it says a derivative can be simplified. They give you the y and don't say what to do with it, but then the very next line they take a derivative, so that's what they mean to do. What is the derivative of that? Y prime. Now, does anyone remember your derivative rules? If not, the top of the page has that. d by dx of arc sine would be u prime, but your u here is just x, derivative of x is just 1. So it would be 1 over the square root of 1 minus x squared. Right? If the u is 1, if u is x, okay? Now, that's the first part. Plus, what do we have here? If you're taking the derivative, what kind of a thing is this? This is written next to that, that means you do what? Multiply. So this will be what rule? The result of multiply. The product rule. This is the product rule. How does the product rule go? First times derivative of the second. The first is x. And what's the derivative of this? Let me rewrite this to be, just this part here, to be 1 minus x squared to the 1/2 power. So what's the derivative of that?
The 1/2 1 minus x squared is negative 1/2. Then we have to, then it'll be times 2x.
Negative 2x. Yeah. Okay. There's derivative just of that part. Okay. Now, without going too much further, notice that the 2's will divide out, and this actually gives you a form that is like this. There's an x hit on the outside here. Just on the inside, it's going to be a minus x over the square root of 1 minus x squared, just to get it back in that form. That's what that winds up being. In the numerator, it's just the minus x, and the denominator is this thing. Okay. And that's going to be multiplied by x, so don't forget that. What's the second part of the product rule? Plus which is, what's the derivative of x?
1.
Yep. times the second, which is square root of 1 minus x squared. Right? Now, let's write what we've got here. Conflicted by whether to leave it in radical or try to go back to exponential. I think radical notation will be okay. 1 over the square root of 1 minus x squared minus, because you have a plus here, a minus there, minus x squared over the square root of 1 minus x squared. Right? Everybody buy that? Okay. Plus the square root of 1 minus x squared. Now, obviously has the least common denominator, doesn't it? Last term doesn't have a denominator, but the first two do, right? And they're the same. There's a common denominator. So we need that same denominator here. The square root of 1 minus x squared. But if we multiply that by that, we have to multiply the numerator by the square root of 1 minus x squared. And what were you saying? Yes. So we have 1 minus the square root of 1 minus x squared minus x squared over the square root of 1 minus x squared. And then, as you said, these two, when you multiply them together, gives you 1 minus x squared over the square root of x squared. And guess what? It all adds to 0. Doesn't it? Because the next one would be plus 1 minus x squared over the square root of 1 minus x squared. And this adds to be 1 minus x squared. Oh, I'm sorry. I thought that was a minus sign in between. It's a plus sign. So that's going to be 2 times 1 minus x squared over the square root of 1 minus x squared. Okay? By that? Okay. Except now, this is the square of that, isn't it? The numerator is the square of the denominator. So let's just make that 2 times the square root of 1 minus x squared. Right? That's your answer. And that's what they got to. 2 times the square root of 1 minus x squared. All right. Now, they say from that you can see that one of the benefits of inverse trigonometric functions, they can be used to integrate common algebraic functions. So they're giving you a hint to the future, okay? Because the next thing we do is going to be, next chapter we do is going to be using this, okay? If I'm not mistaken, maybe it's 2 chapters away, but we'll come back and use that, okay? So let's do, are there any more questions about that one? Okay, I'll hold on for a minute. Got it? Everybody got it? Okay. Okay. All right, let's do example 6. Boy, there's a part of me that just doesn't even want to deal with this, but let's do it. Analyze the graph of y is equal to arc tangent, I prefer inverse tangent, but arc tangent of x squared. For the life of me, I don't know why they're not saying arc tangent squared of x, because that's how they usually write it, but I guess that gets too confusing, so it probably is simpler to do it this way. All right, when we say analyze the graph of it, usually that means you have to graph it, kind of, doesn't it? And that's why I didn't even want to get into this, but here's what I would do to graph that. I would first graph the arctangent of x. Okay, can anyone tell me about the graph of the arctangent of x? Anything at all? Maybe a value or two.
No, it can't be with half times.
Right. The y value can't, because the c, now, okay. Oh, man. Okay, we're not doing y here. We're doing this. And if you want to make that a different value, call it theta, or something like that. Theta is equal to arctangent of x. How does theta look? It can't be the half pi, because theta is the angle. This is an inverse tangent, or an arc thing, so this is the number. The answer to that is an angle, okay? And the angle can't be a half pi. So that is the way to begin, and that would be on this graph here. And then your y is going to be an angle squared, which to me, that's one reason I didn't want to do this. So this is going to be pi halves. This is going to be minus pi halves. And if you were doing the inverse tangent, so I'm going to do that first. This is a horizontal asymptote. That's a horizontal asymptote. Now these horizontal asymptotes cannot be crossed. A lot of times they can. So the what I'm graphing here is theta is equal to inverse tangent, or arc tangent of x. Okay? It goes through 0, 0. At pi fourths, it's going to be 1. And at minus pi fourths, minus 1. And this is how it looks. All right. Now, the reason I did that is so I could square it. Okay? And if you square 0, and so I'm going to do this in a different color. You pick me a color. Anybody? Red. Okay. If I can get it to come up. There it is. 0, 0 will still be there, right? Because you're just squaring that. This value here is pi fourths. Okay. And when the y is equal to pi fourths, you square that. Your theta is equal to pi fourths. You square that, and your y will be pi 16ths, will be 1. So this is pi fourths, pi eighths, pi 16ths. That will be 1. Okay? A minus pi 16ths. Okay? I want to make sure I'm doing this right. Okay. When x is 1, y theta is pi fourths. So when x is 1, this thing in here is going to be pi fourths. Square that, and you get pi 16ths. So the y value is pi 16. I got it right. Okay. Now, and if you square this one, you also get pi 16ths, because you square a negative number and it comes up positive. Okay. Now, I guess you sort of have to take my word for it. The function does something like this. and something like this.
Almost like a reverse scale.
What's that?
Almost something like a reverse scale pattern.
Yeah, it kind of looks like an upside down bell curve. You're absolutely right. Its height is pi halves, from baseline. Okay, because you see all these values when you square them, they go positive. Right? And this 0 stays 0. To square a very small number, it gets even smaller. To square a large number, and it starts getting bigger. So anyway, that's about what it looks like. Okay. Now, that was just to get an idea of what it looks like. They show you in the book, and I'll let you look at that, and it'll be fine. Okay. But I messed something up, I think. Yeah. This is example 6 on page 377. What'd you say?
I was saying you have reports of inflation in your lowest community.
I can't hear it, sorry.
You have reports of inflation in your lowest
Yeah, we're going to get to that. But what I have messed up in the graph is I have to square this pi halves. It's not now going to pi halves as a horizontal asymptote. It's going to pi squared over 4. And pi squared, because pi halves is larger than 1, pi halves squared is greater than, so that's going somewhere up here. This was at about 1.5, because it's close to 3 halves. And 3 halves, when you square that, it would be 9/4, so it would go up to 2 1/4. So this is, up here is where the horizontal asymptote will be, somewhere up there. So even though it comes here, and it takes a long time to get there. I mean, a long time, as you see in the book. So don't sweat too much my drawing. I had it going to pi halves. It's not going to pi halves. It's going to pi squared over 4, which is something close to 9/4, which is 2 1/4, something close to that, but not exactly. Okay, but that's sort of beside the point. Okay, that's just what it looks like. Okay, when it says analyze the graph, what it means by that is determine if it has a max or a min, determine if it has inflection points, determine those kinds of things. So, how do we determine the extreme values, the critical values for this? You remember that? Cal 1? Let me go back to my dark color. How do you find the critical values? Nope. What's the Jesus answer in Cal 1? Take a derivative. Very good. Okay. For those who weren't in my Cal 1 class, I'm sorry if it sounds like I'm being sacrilegious. I'm not trying to be. It's I give the example of at church, our church and a lot of churches, I think, have a children's church, sometime before the real sermon starts. All the kids go up front, and the pastor or some leader stands up there and gives them a little lesson, and then lets them go out to do other things while he does his real sermon. So they almost always start with some question. Okay, and the kids sit there, and when there's too much silence, usually a little kid in the back, usually it's a boy, it seems like, says, "Jesus." He's figured out that any question you're asking in church, if you give Jesus an answer, it's going to be okay, because that no one can say that's the wrong answer, can they? Okay. So anyway, he says that, and then they have to figure out a way to make that okay as an answer. Yeah, he throws the adult off really badly. But so that's what I say. What's the Jesus answer in Cal 1? When I say, and how do you do this? Usually it's take a derivative. That's going to be the answer. Just how I always would do it. Cal 2, it's a little harder. It might be integrate. It might be something else. But Cal 1, it was take a derivative. Clark was in my class, so you remembered that. So let's take a derivative of y prime. What would that be? There's your y. What's y prime? 2 times arctangent of x times the derivative of arctangent of x, which we just did. Well, no, we didn't. We did arctangent derivative of sine. Right above there, you'll see the derivative of arctangent of x, which is 1 over 1 plus x squared. Okay? So there's the derivative. Now what we got to do is set that equal to 0. You take a derivative, set it equal to 0, that finds your critical values. Well, your numerator is 2 times the arctangent of x, and the denominator is 1 plus x squared, right? So where that's going to be 0, who cares what the denominator is? Okay? Doesn't matter. It's where that numerator is 0. And where is arctangent of 0 equals 0? At 0. So this is going to be, this is 0 at x equals 0. So there's your critical point. 0, 0, critical point. Now, if you did not have this graph to look at, you can look at that and say it's going to be a minimum value, and that's the only minimum value we're going to have. Okay? Because up there it's approaching 0, but never gets there. It's always slightly negative. However far you go out here, it's always slightly negative. Over there, the derivative is always slightly positive. It never flattens out completely. It gets closer and closer to 0, but never there. That's the only place the first derivative is going to be 0. Tangent 0. Okay? Now we can see that on the graph. Now I'm sort of regretting I did the graph. But what we know from the graph it's a minimum. Okay? But we wouldn't know that otherwise unless we did what? All we had was the function value without the graph of it. What would we do next? This is almost the Jesus answer of the previous one. Take another derivative, which would be the second derivative. Exactly. Okay? Now, since your first derivative is that, your y double prime would be what? Ooh, boy, what kind of rule do we have here? A big boo hiss. When you divide, what's your answer? Quotient rule. How does the quotient rule go?
D high minus D low. Or,
Okay,
no, low D high.
Low D high. Start low. Okay, so low D high. Low is 1 plus x squared times the root of the numerator. Well, that's going to have a 2 in it. I know that. And what's the root of arctangent?
1 over.
Yes, 1 over 1 plus x squared. Huh. It's just going to be a 2 for that part of it, isn't it? Okay. Minus.
High D low.
Okay, high D low. Okay, that would be 2 times arctangent. That's your high part of x. Times the root of the denominator. What's the root of the denominator? 2x. Okay. So, over what?
Over low, low.
Low, low. So that would be 1 plus x squared squared. Okay. All right, let's see what we got now. That's equal to 2 minus 4x times the arctangent of x. That's ugly. Okay, arctangent of x over 1 plus x squared squared. Okay. Now, when x is equal to 0, which is what we're interested in right now, just to see if this is concave up or concave down, or neither, okay? We know it's concave up. We can see that. But if we didn't have the graph, this is what we'd look at next. Plug into 0 here your critical value, and this will give you 2 minus 0 over 1. That's a positive 2, so it's concave up. So that makes that a minimum. Okay. We knew that, but this just converts it. Okay. When it says analyze the graph, we have a minimum at 0, 0. That's the first thing to note here, minimum 0, 0. You got the minimum from your first derivative setting that equal to 0. You got the critical value, and then the second derivative, the sign of that told you whether it was a minimum, maximum, or neither. Okay. So, the next thing we look for are the Marcus said before, what do you call the what? Yeah, but you said it earlier, way earlier. Second?
Points of inflection.
Points of inflection, which would be where the second derivative is equal to 0. So now we have the second derivative here. We're going to set it equal to 0. And again, it doesn't matter what the denominator is doing, does it? That's not going to affect. It's only what the numerator is doing. So we have 2 minus 4x times the arctangent of x is equal to 0. Well, that says that 2 is equal to 4x times the arctangent of x. Okay. Now, let's divide both sides by 4. So you get x times the arctangent of x is equal to 1/2. Now, that's a pretty miserable equation to try to solve analytically. So what you usually do is get your graphing calculator, plug that in, and find out where it crosses x equal or y is equal to 1/2. I can't. Let me see if. Okay, what they use is Newton's method. Okay, and which is basically using a graphing calculator. Okay. I didn't want to do that at all, but they occur when x is about 0.765. So, frankly, from here on, it's all graphing calculators or something like that. But you can tell, here we have concave up, here we have concave down. Somewhere in between, it changes from going up to going down. And I'm going to go somewhere about here and here, okay? And these would be your x values, which would make that true. And they tell you that is where x equal 0.765. Okay. And frankly, the rest of it just sort of a pain in the neck. But I'm sorry, I didn't say it that way, did I? They analyze where the horizontal asymptote is going to 0, and they just sort of pluck it out of the air and say, I think the safest thing to say is where this thing is squared. So pi squared over 4 squared. And rather than doing some analytical thing, it's just that. Okay. And we already had identified that. So they show the picture here, and it takes a long time for it to approach that horizontal asymptote. So again, I didn't really, but just to remind ourselves, how do we analyze the graph? Take a derivative, set it equals 0, find your critical point. Those are your critical points. Determine whether the maximum or min from your second derivative. And while you got your second derivative, set it equal to 0, and that gives you your points for the reflection. Okay. then from there on, that's most of what you need. If you have any vertical or horizontal asymptotes, know what they are. Okay. All right. Now, example 7 is maximizing an angle. And this is not on the slide set either, so any questions on this before I delete it? This is a pain in the neck problem, but, you know, not a bad one to review. Okay. Maximizing an angle. And by the way, if you go to this book's website, larsoncalculus.com, you can see an interactive version of this type of an example. So not a bad idea to do. Okay. A photographer is taking a picture of a painting hung in an art gallery. The height of the painting is 4 feet. Okay. Do you all have books? You don't? Oh, yeah, you do. Okay, you don't have one. All right, let me draw the picture for you then. I was hoping all of you have a book so I didn't have to draw this, but I'll try to do it. Here's a floor. Here is a painting hanging on the wall. And the height of that painting is 4 feet. That's a big painting.
It's like a painting of Picasso.
Yeah. All right.
Or Bob Ross.
Actually, that's including the frame. Okay? It looks like to me. The height of the painting is 4 feet. The camera lens is 1 foot below the lower edge of the painting. So your camera lens is 1 foot below the lower edge of the painting. So there's your camera lens somewhere down there. Okay? Now, from a different perspective, here's the camera. They're going from top to the bottom of the picture. Okay? How far should the camera be from the painting to maximize the angle subtended by the camera lens? Okay? That's what I was drawing here. Here's your angle theta. Okay? And you want to maximize that angle. Okay? Now the angle's going from the top of that 4 feet to the bottom of the 4 feet, but the lens itself is 1 foot below the lower edge of the painting. So this is another foot here, okay, below the lower edge of the painting. All right. Now, the question is, how far should the camera be? So here's the X here. This is what we're looking at. How far should the camera be from the painting so that you maximize that angle? Sure, you could get the camera way off here, 1 foot below. Let's just imagine. Gracious. All right. This is going to be a foot. Just make it easy. Let's say that's a foot. It's not 2, 3, 4. So you're going from here to there. The camera's going to be down here somewhere. Okay? And you're wanting to get, okay, if you're way back here, it's real easy to get back. But you want to see how far you can do to get the maximum angle here and from there, and you're 1 foot below. That's what the picture, the deal is here. Okay. Now, do they give you anything else? I don't think so. Okay. I'm sorry, I did the wrong theta. This is the angle beta, not theta. They have another angle here from the bottom of the figure. Remember, the camera's there, so with 1 foot right here, okay, this is the angle they're calling alpha, okay, and the angle theta is the angle from the horizontal to the top. So this is the angle theta. Why they named it this way, I don't know. I would have put that alpha and beta and then had the theta be the difference. But they're having theta be the difference between theta, beta being the difference between theta and alpha. So, goodness, I'm even getting myself crossed up. So that's what we're trying to maximize. What a pain problem this is, okay? Now, what you're dealing with here then, and my picture stinks, and I admit that, this is the angle theta from the horizontal, which is a foot below. So you have a 1 foot here, then a 4 feet there. Now, to get right angles out of that, you have the angle alpha, which is the one to the little one. Theta is going to be to 5, okay? And beta is going to be the difference between the two, okay? Now, this is your x down here, how far the camera is away, okay? So this is 1 foot here. X is the distance it is away. So this angle alpha that you're dealing with here is tangent of alpha is equal to 1 over x. Okay? Where theta is the angle beneath the bottom of the picture. Tangent of theta, which will be to the top, that's going to be, this side over here is now 5. That'd be 5 over x. Okay? Now, to get that in terms of, and what we have here, the angle we're trying to maximize is beta, and beta is going to be the difference between theta and alpha. Okay? So, alpha is equal to inverse tangent. I'll prefer it this way, but the book doesn't, of 1 over x, and theta is equal to inverse tangent of 5 over x, if I could write, and you take the difference of those two, beta is equal to theta minus alpha, which is inverse tangent of 5 over x minus inverse tangent of 1 over x. Goodness, my stomach's growling, I don't know why. Okay. So there's what we're trying to maximize, that beta. How do you come up with a maximum?
Take a derivative.
Take a derivative. Sounds like a winner to me. Okay? So your beta prime is going to be derivative of that. Okay. Ugh. Derivative of arctangent, if you look at the thing above, is your u prime. Where your u prime is 5, your u is 5x to the minus 1. So u prime would be minus 5x to the minus 2. Okay? So that's your numerator, and your denominator is 1 plus that thing squared. And this turns into a real nightmare of a set of equations. And here's what I'm going to say. Go to larsoncalculus.com and watch this, okay? We could do it. It's going to take us most of the rest of the class. Not really, but an awful long time to do it. More time than we really need to spend on it. But that's how it sets up, and you go from there. Okay, let's get to the bulk of this. Let's get off of these. And by the way, your answer comes out being 5 over x to the minus 2. Okay, so that's your numerator, and your denominator is 1 plus that thing squared. And this turns into a real nightmare of a set of equations. And by the way, your answer comes out being happens to turn out being x equals the square root of 5. And there's the angle would be about 42 degrees. But let's get through with that. That's way too much time. Review of the basic differentiation rules. Elementary function is a function from the following list of one that can be formed as a sum, product, quotient, or composition. That means, compose two functions of any of these. This is an elementary function. Algebraic functions or your polynomial functions, very easy to do. Rational functions, they get a little more difficult because you've got ratios and variables in the denominator. So you got that to worry with. And functions involving radicals. Those are your algebraic functions that constitute an elementary function. Sum, product, quotients, or composition. The transcendental functions would be your log functions, your exponential functions, your trigonometric functions, and inverse trigonometric functions. Okay? We've done these two in this chapter. We've done these also in this chapter, these some too. But we already knew our trig functions, derivatives and those kind of things. The inverse trig, that was new. Inverse trig functions, their derivatives were new this time. These, hopefully you got down here. You know the derivative of that, easy derivative of that. It's a quotient rule, but it's not that bad. Radicals, change them to exponentials, you know how to do all of those. Okay? So, with the differentiation rules introduced so far in this text, you can differentiate any elementary function. Okay? You use product rule, quotient rule, and your chain rules. For convenience, these differentiation rules are summarized here. Your elementary functions. Now, u is any elementary function u, okay? And c times u, derivative of that would be c times derivative of u. Now, they're not saying how to do that, but they're saying you know how to differentiate all of those elementary functions. And we talked about it. The sum or the difference. This is a constant multiple, sum or difference. That du plus or minus, u prime plus or minus v prime. Okay, product rule. First times derivative of the second plus second times derivative of the first. We know that. Quotient rule. Low d high minus high d low. D means take the derivative over low end. Okay? Know how to do that. Derivative of a constant is always 0. Derivative of the power function is in the exponent times the function, whatever that is, times to the n minus 1 times. It's just a chain rule. Okay? d by dx of x is 1, wherever. Why they went from u's to x's, I'm not sure, but they did. That's 1. Then they went back to u's. It seems like they should have done, well, I guess they just showed something. Oh boy. Nothing was said about the absolute value function. It's just a piecewise defined function. And it just happens to turn out being this. d by dx of absolute value of x is absolute value of u, u over absolute value of u times u prime. Chain rule is in there. The part that you're probably not too certain about is that well, just think, u is going to be the same as x here. So that's going to be this on this side. U will be minus x on this side. So that would be x over absolute value of x. If x is positive, then these are the same, and you just got 1. If x is negative, then this is negative, but that's still positive, so you have the negative 1. So that really does give you the same answer. And here's the two that we did in this chapter. d by dx of log u is u prime over u. d by dx of e to the u is e to the u times u prime. So it's just 1 over u of derivative of log is 1 over the thing times u prime, and derivative of e to the anything through that. Okay. That's just a review. Oops. And more. Okay. Sorry, I forgot. Okay. Any other base, logarithm base, the u prime is still up there just like it was before. And now we've got a 1 over u, but you also have 1 over log a. Okay? So the difference in that and the log function is this is just u prime over u. The next one would be u prime over u, but then you put a log because you have a different base there, log u, a in front. And that's right here. Natural log of a, not the basic log, the common log of a, or log base a. Okay? And d by dx of any other base to the number u. If this was e to the u, it would be e to the u prime. A to the u is a to the u prime, and then you put a log a in front. Whereas here you divide by it, there you multiply by it. Okay? Just like you do with ln's and x's. Okay? And then d by dx, we know these, cosine u prime, minus sine u prime, secant squared u prime, minus cosecant squared u prime, secant tangent times u prime, minus cosecant cotangent times u prime. And then the inverse functions, u prime over the square root of 1 minus u prime, and this would be minus u prime over the square root of 1 minus u prime. U prime over 1 plus u squared, minus u prime over 1 plus u squared. U prime over absolute value of u times square root of u squared minus 1. So these are reversed from that. And minus. It's the same thing. I look them up. I don't ever try to memorize those others. You just don't use them often enough to make it worth me to spend time memorizing. Okay. In fact, I don't ever memorize. If I use them often enough, I get to know them. So, homework exercises here. Whew, goodness gracious. Do number 5. Do any of the odds 7 through 13? They're all, oh, and by the way, number 5 is at calcchat.com. The answer is also in the back of the book, but worked out solutions calcchat.com. Any of the odds 7 through 13, they're all at calcchat.com. 7's at calcview. Do either 15 or 17 or both, they're both at calcchat. Do any of the odds 19 to 23, they're all at calcchat. 21's at calcview. Do either 23 or 25 or 27, they're both at calcchat. 25's at calcview. Do any of the odds 29 to 35, they're all at calcchat. Do 37 or 39 or both, they're both at calcchat. 37's at calcview. Do any of the odds 41 to 55, they're all at calcchat. 43's at calcview. Do any of the odds 57 to 61, they're all at calcchat. 57's at calcview. Do either 63 or 65 or both, they're both at calcchat. 67 or 69 or both, they're both at calcchat. 67's at calcview. 71 or 73, they're both at calcchat. Try doing 75, it's a calcchat. And either 77 or 79, those are exploring concepts. You don't have to do those if you don't want to. You don't have to do any of them if you don't want to, but don't get too bogged down with them. See what at least a cursory look will give you. 81 should be at calcchat, and then there's 2 true false, 83 or 85. They should be at calcchat. Then applied problems, any of the odds 87 through 99. Now some of the later ones of those are proofs like 99. 97's a lot like that maximizing an angle we just did before. Boo hiss, okay. And some of the others like 93's a proof. 95 describes a graph. So you choose which ones of those, if any, you want to do. All right. Now, how are we doing time-wise? Oh, we got plenty of time. Don't we? Wait. Or do we?
Yeah.
Huh?
We're at 11:40.
11:40, yeah. I thought we had plenty of time. Okay, I have to stop and think what time it starts. Yeah, okay. What's that?
They skipped over Galileo, didn't they?
I can't hear.
I was saying they skipped over Galileo, I think. Or someone from the book.
I'm sorry, I couldn't understand what you said.
I was saying I think they skipped over someone from the book. Yeah.
Oh, about a paper topic?
Yeah.
Okay, did I skip that?
Well, it was going to pop up in the slides.
Yeah, I'm sorry, there he is. Galilei, or however you say that. We think of him as a physicist, but he was, as they say here, Galileo's approach to science departed from the Aristotelian view, Aristotle's view, which was sort of thinking through things, describing it, and Galileo quantified everything. And so you can't just count him on physicist. He's also quite a mathematician as well, yeah. So he's a potential paper topic there, as could be possibly Aristotle as well, or a comparison of the two. You can come up with several potential paper topics. Thanks for pointing that out. All right, now let's see. I think I was in the process of ending this and going to 5.8. This is the last section in Chapter 5, so we should be ready for the test really soon. So try to get Chapter 4 test in as soon as you can so we can go on and get this one done. Goodness gracious, this has been way too long. All right. Chapter 5 is logarithmic, exponential, and other transcendental functions, as we've already seen. 5.8 is inverse trigonometric functions, integrations. Okay? We'll integrate functions whose antiderivatives involve inverse trigonometric functions, just undoing what we just were doing. And we'll use the method of completing the square to integrate a function. That will be a little different. And then we'll review the basic integration rules involving elementary functions. So, integrals involving inverse trig functions. And these follow directly from the derivatives. Okay, so that's why I wanted to go over the derivative rules so we can turn around and do these. Derivatives of the 6 inverse trigonometric functions fall into 3 pairs, and each pair of the derivative of one function is the negative of the other. So, derivative of an arc sine, okay, derivative of the inverse sine, we already did this one. 1 over the square root of 1 minus x squared. This is the sine of x. If that was a u, it would be u prime over 1 minus u squared. Okay. This is just simply being x's here. Arc cosine, exactly the same as this, except the minus sign. Now, if you think about that, what does the arc sine function look like? It looks like that, right? Always positive. Arc cosine function, that, always negative. But they have the same slopes everywhere. They're just, yeah. So, all it is a change of sign. Okay? Now, when listing the antiderivative that corresponds to each of the inverse functions, you need only one member from each pair. Okay? So, if you're doing the antiderivative of this, you can just, it's convenient just to use arc sine rather than negative arc cosine. Because look, that's, you know, it gives the same thing, it just introduces a minus sign. So when you see this, think arc sine, inverse sine. Okay? Don't even worry with inverse cosine. And guess what? Same thing holds for tangent and cotangent. They look a lot alike, only with a minus sign. So just forget about it and just do this. Now, they've done 2 things here. Gone from x's to u's, 3 things. And gone from 1 minus to a minus, a squared minus. Okay? So, why in the world are they doing this thing? I don't know. We're going to turn around and do this same type thing a little bit later, using a different way that you don't have to memorize anything. Okay? But if you like to memorize this, this will be fine. I mean, it's perfectly okay. We're going to do these later. So I'd say let's not even bother with them right now. Okay? So these are those three. If you want to jot these down, write them down, keep them someplace you can always go back, or just plan to look them up in a table. We're going to do these analytically a little bit later with no memorization involved. So I'm just about to talk myself out of doing anything in this section. Okay? What you think? Wait until we hit them later, or you want to go and do these now?
Well, we'd be ready for a test if we did them later, wouldn't we?
Yeah? And I don't have the test ready. I'll give it to you next time. Is that okay? Okay. So let's just see what the slides are. They give you the answer to them, so I don't know what they're doing. They're just saying, plugging in what you already had before. The A was 2 because it was 2 squared, and that would just be x over A, and that would be x over 2. And this will be an inverse tangent. You know, that's how you get there. So that would be, our tangent will be your answer there, with all the appropriate stuff in front. We'll figure out how to get all those things later without having to memorize, okay? And that will be an inverse secant, okay? Just recognize the form. Don't worry about the other things till later. Now, completing the square. What are they meaning here? Completing a square helps when quadratic functions are involved in the integrand. So if you have something like this in the integrand, it can be written as a difference of 2 squares by adding or subtracting. And y'all, you've done that before, right? Take half of b, square it. Okay. You did this back when you did the quadratic formula. Okay? This is, once you did this and then did quadratic formula, you thought, I'll never have to complete the square again. Well, you still do. And you probably had to other times. And basically what it's trying to do is going from here to a form where you can use inverse sine or cosine, or actually in this one, inverse tangent, okay? So you complete the square, take half of this, that's minus 2, square it, and you get plus 4. So you add 4 and also subtract 4. There's where you add 4, there's where you subtract 4, the 7 just is out there. This is the perfect square of x minus 2, and this is the plus 3. So you have x plus 2 squared plus 3, and that is a form that you can do if you're taking the integral of it. That would be an inverse tangent. That's your u squared plus a, and if you're doing the integral of that, and we'll be doing this a little bit later. A is the square root of 3, so that's the inverse tangent with the thing in front, underneath, and all like that. We'll see how to do this a little bit later, and we will again be completing a square with it. So don't sweat this for now. So here's the basic integration rules. This is not a bad thing to review. The integral of k times the function over k on the outside, the integral of the function of u du. Okay? Integral of the sum or a difference is the sum of the difference of the integrals. Okay? The integral of du is just u, and these are all indefinite integrals, so you'll have a plus c when you actually get to this. Here, if it's just changing integral form, you don't need the plus c yet. If you're given the answer, then you need the plus c. And this is your power rule, so it would be you get n plus 1 over n plus 1. You know, up that by 1, divide by that, and yeah, just like we've done. That doesn't work for n equal minus 1, obviously. And what would that give you if n was minus 1? If this is u, that's the log. Exactly. Okay. And there it is right there. Okay. Log absolute value, you have to put absolute value, but you can't take log of 0 or a negative number. And this is my favorite of all time. Integral of v du is e du, not k, plus c, of course. And a du would be just 1 over log a du. integral of sine will be minus cosine. These are just good old integration rules. More of them, cosine and sine. Because the derivative of sine is cosine, then this gives you that. Because the derivative of cosine is sine, the other one had the minus sign. This is. Now these again, there's lots of ways you can express that. That would also be the same as the log of secant. It's like log of cosine is fine, or log of minus log of cosine, or log of secant. So again, you can look these up in a table if you ever need it. This would be the log of absolute value of sine plus c. That would be, remember, antiderivative of secant is log of secant plus tangent. These are just those little weird ones we did before. Cosecant would be the same as that, only opposite sign. Same form of that, but opposite sign. Secant squared is tangent, cosecant squared is minus cotangent. Secant tangent would be secant, and cosecant cotangent would be minus cosecant. So that's your inverse sine, inverse tangent. Inverse. Yes, sir. Hey.
So I wanted to kind of leave it open, like when he said, I think he's coming about 12. But
okay. Till then, or just leave it open?
Oh, before then, he might get here early.
Okay.
So
just try to remember that.
Yeah.
Leave it open.
Yeah.
Okay. All right.
I'll get back in.
Okay. All right. But those, they're just a review of all those. You can always look them up in a table. Okay? So, just for funsies, this is going to be an inverse secant type form. So that's going to be inverse secant. This is going to be, what would you do here? Any ideas? Again? Just do a substitution. But this thing in here be u, and it just works out. Nothing that we did in this section, okay, is part of the text. It's just a good old substitution, right? Okay. Now, once you do the substitution, you're going to have a log function. Okay, so yeah, it will lead to something that we did in this section that will lead to a log. This one, however, will be a that had absolute value x in front, that would be a like that. Without that, you're going to have to flip that around and do the minus of. No, I don't know if you can legally do that. This, I think all it says, find as many as you can. This one, nothing in the section. In fact, I'm not sure anything would work on that one. Okay. I'm sure something would, but nothing we've studied so far. Okay, that would be the arc-secant rule, like we said. This would be a substitution. And then it'll lead to the power rule, okay? And that's pretty complicated, but it's doable, okay? You cannot find that last integral using any technique studied so far. That's what I said. Nothing. Okay. All right, and that finished chapter 5. All right. Now.
So we're on to 5.9.
Oh. There is a 5.9?
Yeah.
Hyperbolic functions.
Okay. No, we're not. And here's one reason. I had just looked at this. There is no, oh, okay. I'm sorry. I did that. Sorry. I just looked at this and said, nope, we're not going to do hyperbolic, so I didn't save them to this thing. So no, we're not doing hyperbolic. I was going to do a slideshow of it for you, but since I didn't put them on the slideshow, not going to do that either. Okay? Now let's see. and there is no 510. Okay, so if you can go back and look at a table of contents, if you don't have one, you can just thumb through. In Chapter 5, we did do 5.1, 5.2, 5.3, though I'm not sure I'm going to ask you many questions on 5.3. I'll evaluate that. 5.4, 5.5, 5.6, 5.7, and I'm not sure I'll ask many on 5.8. So basically, I'll evaluate that, and I'll tell you which sections they're going to come from. Not going to do any on 5.9. I'll tell you that. Okay. So when I get the test ready, I'll tell you which sections to go to. And right now, my inclination would be only one problem from 5.3 and one from 5.7. And probably one from 5.8, one from 5.6, 1, 2, 3, 4. Okay, one. Okay, 2 from 5.1, 2 from 5.2. That'd be 4, 5, 6, 7, 8, 9, 10. Yeah, and one from each of the others. It's probably what it's going to turn out being. And if I do anything differently from that, I'll let you know. Chapter 6, the reason I left that off is that's differential equations. So let's not even worry with that. That's going to be a course you take later, okay? So let's now go to 7, which is where I often start this, but since there was some request at the very beginning. Now, anything in between, and going back to what DeMarcus did before, I just happened to flip a page and saw one of those features of some mathematician or a scientist or something there. And now I can't find her, but it was a female mathematician, although I just happened to notice it was a woman. I didn't even stop to notice who she was, but those are all legitimate paper topics. Anything in here would be legitimate paper topics. Oh, let's go back to Chapter 5 again. I meant to do this before I left it. Okay? The review exercises, the odd numbers are at calcchat.com. All the answers are in the back, but if you wanted to do some of those just to get a little more thing, I would do any of those odds. Okay? 1, 3, blah, blah, blah. Okay. What's that?
I said it was already open.
Oh, what? Yes, I forgot to watch it. So it may wind up being open on Wednesday if I forget to look at it. Usually I go in there for something and lock, but evidently I didn't use a lab or something, so I didn't do it. So. All right. Sorry about that. Okay. So any of those odds in the review exercises are good, would be good to do. Okay. Now let's move on to 7. There she is. Anna Johnson Bell Wheeler. I didn't think I recognized her. Awarded a master's degree, 1904 from University of Iowa. She worked on integral equations while studying infinite linear. Just mentions that, doesn't say what. The thing is, 1904, there weren't many women getting master's degrees anywhere, and there sure weren't many getting master's degrees in mathematics. Especially on a topic, the extension of Galois theory of linear differential equations influenced by David Hilbert. Wow, that's pretty deep stuff for anybody, okay? So, how are we doing? Almost out of time?
Yes.
Okay. Just, what's that? What page is what? Oh, her, that woman I just said? Oh, goodness, where was it? It was on page 432. And there may be others in there. I'm just saying that anything you see in between, you can use those as paper topics too, even if we don't go over it in class. Okay, we got 5 minutes. 5 minutes, right? Okay. We're going through from the current slide. Okay. Chapter 7, applications of integration. So it will be chapter 8 before we do the things I was just talking about. We're going to pick up later. But this is going to be pretty much an extension of what we were doing before we got onto that mess, that stuff. Okay? Area of a region between two curves. The one from chapter 4 we were talking about, there was an area of a region, right? So we're going to be doing things like this. Only now it's going to be between two curves rather than between a curve and an axis. Okay? So find our objectives here will be to find the area of a region between two curves using integration. Find the area of a region between two intersecting curves using integration. That sounds like almost the same thing, but not necessarily true. And describe the integration as an accumulation process. Oh yeah, that sounds exciting, doesn't it? All right. With a few modifications, you can extend the application of definite integrals that we did in chapter 4 from the area under a curve to the area between two curves. So it's a pretty simple process. Consider two functions, f and g. Here's f, there's g. Okay? We're going to consider these on a certain interval a to b. And I'm going to tell you what is going to constitute part of that interval. We're going to make sure that in that interval, f is always greater than or equal to g. So this a could be here, it could be here, 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 b could be anywhere here, but a couldn't be anywhere past this place where they're equal, b couldn't be any place past that. You always have to have the one greater than or equal to the other. If you got out here and you try to do f different, you're going to get negative areas. We don't like negative areas, okay? So we're going to stay between the intersection points, okay? So that's where the A to B is going to be. It's going to be between, this is the minimum value for A, there's the maximum value for B. Any A to B in between there will be fine, okay? Also, the graphs of both F and G lie above the x-axis, and the graph of G lies below the graph of F. Okay. Now, the first part is not necessary. They both don't have to be above the x-axis. You could take this thing and have part of this be there, or the whole thing down there. Everything we do is going to do. For now, we're going to keep everything above the x-axis so we don't get too wiped out by it. But after a while, we'll see we can generalize it even below that. But we are always going to have f of g lying below the f of x. That's why I said you can't go past this point for A or that point for B. Any other A, B, or B. Okay. Okay. Now, you can geometrically interpret the area of the region between the graphs as the area under one graph. Okay. Here's the area under F is here. We did that in chapter 4, right? Here's the area under G, okay, in that same interval. And let's just subtract this from that, you're left with the difference here. So guess what that tells you? The integral of the difference of two functions is the difference of the integrals of those two functions. You know what? We saw that same thing in the table of integration just a couple slides ago, back at the end of chapter 5. Okay? So this is nothing really all that new, especially if you did chapter 5. Okay? Now I'm beginning to wonder if it was even necessary, but I thought it would be helpful. Last time I didn't, this time I thought we'd try. It took too long, so I'm not sure what I'm going to do next time. I'm not teaching this one. But anyway, to verify the reasonableness of the results shown there, you can partition F and just do it this way, which actually comes out being the same thing. Remember how we did areas? We split the areas into little rectangles, right? Little dx here, you know, the rectangle. The rectangle from here to here, that would be from f of x minus g of x, dx, that in this sum those, integrate those from A to B, you get the same thing. So yeah, it's exactly what you got the other way. Then as shown here, sketch a representative rectangle of width delta x. The height would be the difference between f of x and g of x. Now, this is with both of them positive. Still work if g of x goes negative, then it would be f of x minus a minus number down here, which would be adding your f of x to your g of x, and that would be between the two. Same thing. And even if the f of x was negative and g of x was even more negative, just has to be less than, then it would be a negative number minus a minus negative number. Still going to be a positive number, okay? So it's going to work okay. It doesn't really matter, okay? That they both don't have to be above the x-axis, okay? It will still work as long as f of x is always greater than g of x in the interval, okay? The area of that representative rectangle that we have there, the height, which is f minus g, at those values, times the width, which is the width of dx. So there we have it. Adding the areas of the n rectangles, taking the limit as that. The delta here, I don't know if you remember, that's called the partition. And they're not identifying anyway, but the partition, the thickness of the biggest piece is going to 0 as the n is going to infinity, then the summation goes to become the interval. Okay? If you're adding up these little rectangles, areas here, summing from 1 to n, and what that goes to infinity, that gives you the interval. That was your definition, because the f and g are continuous on A to B. You know, they showed that. The difference is continuous on A to B. The limit exists, and that limit will be your interval. And n goes to infinity there. I think we did run out of time now, didn't we?
Yes.
Okay. So we'll start next by reviewing that statement there, and we'll move on. Sorry, I probably ran a little over that time. All right, good deal. Thank you. Okay, you didn't mess with number 2, huh?
You know how to do them,
Okay.
and without having to, it's just killing me not having the book, so I don't have anything to look at.
Sorry. I'm trying to remember, why didn't you? You only got up the section you needed?
Yes, sir, and I can't figure out what I've done with chapters
Oh, the
1 through
others
4.
of okay.
And,
Yeah.
I mean, I'm sure I've got them home somewhere, but where I can't.
I see.
I
Okay.
can't find them.
Well,
So,
I know you must have told me that before. You'd have been welcome to take pictures of this or whatever you wanted to do, but you want to still, or?
no, sir.
Okay.
I'm ready for chapter 5 now.
Okay. I think you'll do okay. All right. Good deal.
So when are we getting the chapter 5 test?
What's that?
When are we getting the chapter 5 test?
Next time. I didn't know we were going to finish today, so I didn't have it ready today. I'll give it to you next time. When am I getting chapter 4 test? That would be my question to you then.
Either Friday or Monday.
Okay.
Because I'm have to be studying this week.
Okay. All right. Well, get them to me, or in the paper too. Try to get that
Oh, yeah.
to me.
I can get you that Wednesday.
Okay, that'll be great.